सोने चांदी के छोटे सरकार प्रोडक्शन करेगी। इस समय बहुत चल रहा है कि आज आपको लग रहा है कि बाहर 2021
So we are not able to hear it.
Welcome back, everyone. We now move into the second technical session of SPECTROMAT 2026. To introduce our distinguished resource person for this afternoon's deep dive into electron microscopy, I invite Mr. Anu Thomas, Assistant Professor, Department of Physics, St. Stephen's College, Uravur.
Good afternoon to everyone. It is my great pleasure to introduce today's speaker, Mr. Anu A.S., who serves as an analytical engineer at the International and Inter-University Center for Nanoscience and Nanotechnology, IUCNN, Mahatma Gandhi University. Mr. Anu brings over 12 years of rich research and technical experience in the field of material science and nanotechnology. He specializes in electron microscopy and advanced characterization techniques such as TEM, STEM, SEM, AFM, and optical microscopy. His work also spans a wide range of analytical tools, introducing XRD, UV visible, DSC, DMA, and TGA, making him a highly uh, versatile instrumentation expert. At IUCNN, he plays a pivotal role in training PhD scholars and researchers in operation of high-end electron microscope and advanced sample preparation techniques such as ultramicrotomy. Beyond training, he actively supports interdisciplinary research collaboration uh, through data analysis, instrument maintenance, faculty management, and laboratory development initiatives. His international experience as a technologist at the Institute of Non-Ferrous Metal, Poznan, Poland, where he worked on graphene-based composites for lithium-ion batteries, further highlights the global exposure and research contributions. He has also authorized research publication in reputed journals, contributing significantly to the scientific community. A life member of Electron Microscope Society of India, Mr. Anu is deeply committed to advancing microscopy-based researches and fostering collaborative scientific growth. Today, we are fortunate to have him um, share his knowledge and expertise with us. I request everyone to join me in warmly welcoming Mr. Anu AS to deliver his session. Personally, um, I have pleasure to share that my name is also Anu. Thank you.
Hello. Oh, okay. Thank you for the kind words. And I would like to thank the organizers of the workshop. And I appreciate the initiative to organize these kind of workshops to strengthen the research of the institution. So today we will discuss about transmission electron microscopy technique. So stuck. ഇതിൽ മാറുമോ ഓക്കെ ഇല്ല കുഴപ്പമില്ല അതിൽ ലേസർ മാത്രം മതി Okay, so today we will discuss about transmission electron microscopy techniques and its sample preparation methods, instrumentation, and data analysis. So maybe you all are very much known about microscopic techniques, maybe optical microscope. So what is the purpose of using a microscope? Sorry? To visualize very small particles or objects that we cannot see with our naked eye. Okay, so that is the purpose of this magnify lens and all those kind of small instruments that we can consider as a microscope. And in case of life science, we are using optical microscope, fluorescence microscope and all. The limitation is we are using visible light there. The probe size is very high. It's about 400 nanometer in range because we are using visible light. That is the limitation if we think about the resolution, because here we are using this transmission electron microscopy for the analysis of nanomaterials. So the size of a nanomaterial, we will consider a particle if it's nanomaterial or not, because if the size is about 2 to 100 nanometer, then we will consider it as a nanomaterial. So if we want to visualize this kind of materials, we should have that much resolution. Okay, so before going to the microscopic technique like electron microscopy, before that we should familiarize about the terms that we commonly used in microscopy. First thing is magnification. So what is magnification? Magnification is the thing that just zoom in or enlarge an image or what we visualize using a microscope. So magnification is how many times we magnify an object. If so 1 micrometer particle in the magnification limit of optical microscope is 1,000 times. Okay. But in electron microscope, it's about 1.5 lakhs times. So magnification is that if you magnify one image 100 times, then the magnification is 100x. Okay. The next thing is resolution. So here you can see, here this is the magnification. This example. Here you can see the eagle head here. But if you magnify it, we will lose some information, but we will get more details about this region where we magnify. That is the advantage and disadvantage of magnification. If you want to see the eyes and you give this, it's like 10x. What will happen if you give some 1000x or something like that? Then you cannot see this region. Maybe you will just see this point only. So that is very important, the selection of magnification. If we over magnify, we cannot get any information. If it is very less, then also we will not get any information in microscope's image. That's so magnification is very important. Next thing is resolution. So what is resolution? Any idea? Because in our mobile phone cameras, we say high resolution and it's like megapixel, gigapixel like that. Okay. So what is meant by that resolution? So we can define it. Any idea? Yes, the two closed points we should show this separately like this. If we have much better resolution, we can show these kind of images. Like in case of atomic electron microscope, we can distinguish atoms. Even hydrogen atom also we can visualize with atomic resolution electron microscopes. Okay. Then electromagnetic, lens system. That is the main component of an optical microscope. So in optical microscope, we are using glass lens. So what kind of lens we are using in optical microscopes? In basic physics, you studied about all those things, right? So we are using convex lens. And the magnification of the microscope, that depends on the focal length that we use. But in case of optical microscope, we are moving lens to adjust the focal length. If we have larger the focal length, then we will get lower the magnification. That is the relation between magnification and focal length. Okay, so next is aberrations. So what is aberration? In optics, this is the major issue that we can compromise with we need to compromise with the resolution, because in theory the optical microscope resolution is about 200 nanometer, because the resolution of a microscope is lambda by 2. Lambda means is the wavelength of the source that we use. So in optical microscope, it's about 400 nanometers, so the resolution should be 200 nanometer. So if in theoretically we could see that much smaller particles with a optical microscope, but we cannot. That is because of these kind of limitations, lens aberrations, all those things. So aberrations means the inability of a lens to focus the source in a single point. There are two kind of operations are there. One is spherical operation. You know, this is a bulb. If it's light, then light is coming like a spherical path, right? So the outer side of the waves cannot focus onto the center point. That is spherical aberration. And you know, if we generated some electron beam or light photons, the wavelength or no, the velocity of all the beams may not be same. So we cannot. It's difficult to focus all those beams to a single point. That is chromatic aberration. So these kind of aberrations are there in our optical system. Because of that, we cannot get this much theoretical values in practice. These all are the basic about our optical microscope. Okay. So if we move to electron microscope, there we are using electron beam. So why electrons? You know, electrons are negatively charged subatomic particles. It's a particle. But de Broglie says that we can have electrons as particle as well as waves. But how? How we can use these waves in a wave nature? In idea, it's a particle. So how we can use these electrons as electron beam? We cannot electron beam in, it's like in normal room condition, because we can just switch on a bulb here in this room and we will get photons like light all everywhere in the room. But if we switch on a electron gun in this room, we cannot generate electron beam there. That is because a electron that is generated from the gun, the next moment it will absorb or scattered by the particles. So there's dust particles or maybe air molecules all over there. So we cannot produce electron beam in this kind of room condition. So we should have very high vacuum condition. Okay. So there are many types of electron microscopes are available. That is depends on the electron matter interaction. So when we generate one electron beam, then it is interact with the samples, that what are the interest of our sample, it will interact with that sample. So there are a lot of other information we will get, not only this transmission electrons. Using those electrons, we will get different many type of information. That for that we are using different types of detectors and different type of instruments. That's why we have different types of electron microscopes. Commonly used electron microscopes are transmission electron microscopes, scanning electron microscopes. Then there are some other spectroscopic microscopic methods like EELS, EDS. And then we use this particle nature of the electron for crystallite analysis, like SAED patterns, selected area electron diffraction, and lattice imagings, like that. So that's why we are using electrons in electron microscope. And the wavelength, we just move from the point, like how we are generating this electron beam. First, we with using an electron gun, we generated, but that may be particles, may not be electron beam. For that, we should have a high voltage acceleration system. It's like in common microscopes, we are using 80 kV, 80,000 volts to 2 lakh 3,00,000 volts. That much acceleration is there. So electrons can run from the source to the accelerator. That is how we are generating electron beam. Okay. That's why if you check over some electron microscope, there is a specific thing is like operating voltage is there. That is, it's like for SEM, it's about 5 kV to 50 kV. In TEM, it's about 80 kV to 300 kV. That is the electron gun and acceleration voltage that we use. And the highly accelerated electron beam having a wavelength of 0.23 nanometer. For a 200 kV accelerated electron beam is having 0.23 nanometer wavelength. So, 0.23 nanometer resolution. The wavelength is in picometer only. Okay. That's why we are using electron beam in high resolution imaging. It's like for nanomaterials characterization. Okay. This is the first electron microscope made by Ernst Ruska, and he awarded Nobel Prize in 1986 for this invention. Also, there is another one Nobel Prize in chemistry awarded in 2017 for radioelectron microscopy. So this is that much potential topic in our scientific society, and it's also useful for humankind. Okay. These are the comparison like commonly used electron microscopes and our optical microscope. In here, you can see this light microscope and transmission electron microscope. In principle, it looks same, right? There is no change. The source is there, condenser lens, sample, then objective lens. In IP side, we are using cameras. That's only different. In optical microscope also, we can use cameras. So in principle and schematic, it's the same. But in case of scanning electron microscope, there is scanning coils because in transmission electron microscope, it's working same with the principle of optical microscope, that is transmit light through samples in optical microscope, and electron microscope, we transmit electron beam through the sample. Okay, so setup everything is in schematic is same, but the difference is that here in light microscope, we are using a visible light or bulb as the source. But in transmission electron microscopy, we are using electron guns. So, as I told you, we cannot generate electron beam in this room condition. So, we should have a very high vacuum system. My vacuum condition should be there. For that, we are using a closed chamber. Okay. Discuss കാരണം PPT അല്ല ഡിസ്കസ് ചെയ്യാനാണ്. Okay, so if you compare with the electron microscope, the light microscope, the instruments are like the parts used are the same. Like we have a source, condenser lens, then sample region, then eyepiece or objective lens, and everything is same. But there we are using in light microscope, we are using visible light, and here we are using electron beam. So just imagine like what may be the possible changes we need to go for a electron microscope than optical microscope. There only change is that we are using electron beam instead of light. So first we need a high vacuum system or high vacuum condition to generate the electron beam. The next thing is lenses. So in optical microscope, we are using glass lens, optical microscope. It's like just a convex lens. It's common, like for telescope, for microscopes, everywhere we are using convex lens. Only change is that the focal length of the lens. Then next is in electron microscope, we are using electromagnetic lens. So what is an electromagnetic lens? This is just a coil. I will discuss this in the instrumentation side. So it's just a coil like our fan or any windings. If we induce some current, then magnetic field will be there. That magnetic field we use for bending the electron beam. Slide change ആവുന്നില്ല. മൗസ് ഉണ്ടോ? ഇല്ല. ഇതിൽ കീബോർഡിൽ ലാപ്പിൽ മാറുന്നില്ല. Okay. So these are the comparison. Like first one is light microscope. No, first one is this one is a light microscope. There's the electron microscope. There we are using photons. There is electrons. So we are using electromagnetic lens to focus the electron beam. So how it is happening? Like in optical lens, the lens will bend the light. Here, this is happening. The magnetic field bend the electron beam. This is how we are focusing electron beam in electron microscopes. Okay. And if we illuminate our sample with electron beam, then all these interactions will happen. Okay. So all these are our area of interest, because in our technique, in transmission electron microscope, normally we are using transmitted beam. So all this part, we can consider this for SEM, because in SEM, scanning electron microscope, we are using scanning coils and we are scanning the surface and we are plotting a 3D surface image. So that is not an actual imaging technique. It's a mapping technique, SEM. But in TEM, it's a direct imaging technique. What is happening is like just projection. So, you know, the projector, if we can place one film is there, then we will get a magnified image on the screen. That is a projection. Also, other comparison is you just think about our medical X-ray. So how we are getting our skeleton image in X-rays, how it's happened. We pass X-ray through our body. So whenever you go to the X-ray lab, there they will change the exposure, depends on the thickness, like if it is a fatty man or the thighs or all. So then they will adjust the exposure to transmit the X-ray through our body. So what happened? Through the flesh, the X-ray easily pass, but for the bone density is high, so X-ray may not be passed through the bone. So they are using X-ray sensitive films, and wherever X-rays, it became dark. So we are getting our skeleton image. That is how X-ray works. The same thing, same principle that happening in electron microscopy, transmission electron microscopy. We are getting a shadow image. Okay, so it should be there in your mind because in image interpretation, it is very important. You see, if you place this is if you place this like this, when we can see the shadow like this. If you place this like this, you will get this as a sphere. So you may misinterpret this is a sphere. That is very important thing in KEM image analysis. So it should be there in your mind. We are getting image like projection. So in which direction we place the sample, our information will be depends on the direction. So that is very important. If you analyze one rod-like material, if it is in a vertical position, you may not be getting a image like rod. That is the major thing. Like there are a lot of errors maybe can happen. And the other thing is that it is a transmission technique. So we cannot say the other particles or something on the surface or on inside on the bottom. We cannot say it's like in the shadow, if you place something on the top, you will not say that the particle is there on top. All those things we will discuss in the interpretation section. So in here, we are using this transmitted electrons for imaging purpose. And there are scattered electrons that has the information regarding our crystal planes because the scattering happening, it's the lattice or the crystal planes act as grid lines. Okay, so we will exactly getting the lattice parameters or crystalline information in this scattered electrons. Then X-rays are there. This emitted X-rays that is using for analytical techniques like EDS. Electron. So that is EDS means energy dispersive X-ray spectroscopy. That's also there in transmission electron microscope and scanning electron microscopes. Because wherever you illuminate electron beams, there we have this characteristic X-ray. That we will explain this in the EDS section. Then these are the construction of a transmission electron microscope. So in here, this is the gun region, and then this is the condenser region. Here is the image sample region. Here is the objective lens region, and then there are a lot of other lens like intermediate lens, projector lens, and all. There are a set of lenses are there. Not only one condenser lens. In condenser lens section itself, there are a array of lenses are there. That is for to control the magnification as well as the aberration corrections. For those things, we are using multiple lens. And then in the objective side also, we have multiple lens. Objective lens also there. And then projection lens, intermediate lens, all are there. The objective lens, there we are getting this image. Okay. But there are different planes. You see, these are the different operating modes. So this is the normal mode, this is the low mag mode, and this is the diffraction mode. Because if we want to analyze one sample, first we should go to the area of interest. For that, we should see all over the sample. So to choose a region, we are using very low magnification. So that is like our optical microscope magnification. So we can see most of the regions. And then we will go to the mag mode. There we can go up to 1.5 lakh times magnification. So in that kind of magnification, we are using for lattice imaging. Okay. And here, this is the selected area electron diffraction mode. If you see in this mode, we are eliminating all these scattered electrons and we choose this on the axis like transmitted beam alone. Okay. So that is how we are getting images. But in SAED mode, we are considering this scattered electrons. So here, this is like the objective aperture is in the axis. Axis means, so if we are it's in the imaging mode, we will call it as bright field mode. Bright field mode, that the source and the detector, everything in the same axis. So we will get bright field image. Bright field image, that's background is bright, image is dark. That is because it's in imaging mode, we are using projection type. So if there is some sample that will absorb or scatter our electron beam, there we will get lower brightness. So that portion become dark. That's why we are getting images in bright field mode. Commonly, we are using bright field for normal imaging. In diffraction SAED mode, we are using that scattered electrons. That is on the other axis. So we are getting dark field image. So dark field image means background is dark and the area of interest or the sample region will be bright. That is the dark field imaging. So on axis means everything in on the same axis. Source, sample, detector, everything same axis. But in SAED, what is happening? Sample, source, sample, then scattering is there. So the beam scattered to other axis. So we place detectors or aperture there, then we collect all those information. Scattered electron information that's carrying crystalline information of the sample. For crystalline sample, we will get selected area electron diffraction spots. Okay. These are the different imaging modes. So in here, you can clearly see that in imaging mode, the incident beam directly comes to the detector. Okay. But in SAED mode, the scattered electrons is blocked with this aperture. And okay, in SAED mode, we will use SAED aperture and we use all these transmitted as well as selected area, like scattering electrons using selected area aperture. It's a very wide aperture. So we will get all those informations. So those informations we are using for high resolution imaging also, because those scattered electrons having our lattice fringes information. So we are using this transmitted as well as refracted beam and taken our FFT to create the crystal plane images. So we will directly get the lattice fringes images. And these are some of the images we will get in imaging mode. Okay. All those are like we are placing sample and then just project, we'll get this kind of shadow images. Okay. This is a cellulose nanofiber image. This is graphene decorated with some AG cubes. And this is the carbon nanotube. This is some AG silver particles absorbed on some other drug material. And those two are zinc oxide. This is zinc oxide rod and this is zinc oxide flower. And then these are polymer nano composite, because in tire industry they are using carbon black in rubber matrix. Like that, in this sample, they placed carbon black. You can see graphene here. So anybody can show this. There are some carbon nanotubes there in the sample. Can you identify? You see here, everywhere there is carbon nanotubes. So in this sample, they put graphene, carbon black, and carbon nanotubes. So this is one of the purpose that what we are going for TEM. So if you have some sample, then what are the information we will get from transmission electron microscope? This kind of images, and then SAED patterns, selected area electron diffraction, that's similar to our X-ray diffraction. Okay, and then lattice fringes images, and then EDS data and yields, electron energy loss spectroscope, spectroscopic data. So those are analytical techniques. These are imaging techniques. Okay. This is how we are getting electron diffraction. So all these rings corresponding to our XID peaks. Yes. So how we are getting these rings in polycrystalline materials. See here, you can see a single crystal material. If it is a single crystal material, our diffraction port is like this. So like this line. Here you can see this. Okay. And this is with a single crystal or single grain. And then the same lattice, it's in the other orientation. What will happen? Here, this is the same crystal plane with in other orientation. So here you can see this like this, and here like this. Okay. So it will combine like this. This is how we are getting SAED pattern for polycrystalline samples. Okay. So this rings corresponds to one peak in XRD, and this is corresponds to another one, and this for another one. Like this, we are getting SAED patterns in TM. And these are the different types. The pattern is depends on the type of or nature of the sample. If it is a crystalline sample, then if it is a single crystalline, we will get line-like structure. Okay, an orderly arrangement will be there. We can see that. But if it is a polycrystalline, then we can see this concentric circle, like many rings will be there. And if it is amorphous, then there will be no concentric circles or no spots, nothing will be there. There is only faded image will be there. This is for amorphous type samples, and this is for polycrystalline. This is for single crystalline. Next, indexing. That is very simple. In polycrystalline sample, you just measure the diameter of the rings, and then divided by 2, you will get the radius. Inverse of the radius will be the despacing. So this is how we are interpreting this SAED pattern for polycrystalline. For single crystalline, we are using some other methods. So there are some softwares you can use for indexing this single crystals. And with that D value, we check this with the ICDD data, we will get the plane. This is how we are interpreting SAED patterns. Okay. So this is the high resolution imaging mode. In this mode, we will get this kind of lattice fringes images. Okay, we can directly see the arrangement. So what is crystalline material and amorphous material? In crystalline material, we have an orderly arrangement of atoms, but in amorphous, we know. So in this, we can see all these are crystalline materials, and here we can directly see the atomic arrangement. Okay, this is what is we are getting in HRTEM. Normal TEM and HRTEM, everything will be same, but because of the resolution and the operation corrections, lens used, pulpis used, we are getting these kind of images in HRTEM images. But in normal TEM, we cannot go up to this much magnifications. That is the different. So next thing is analytical electron microscopy. That includes our EDS. So you know how we are getting this elemental information in EDS. In EDS, we illuminate the sample with electron beam. Then, this shells of atoms. So this is the incoming electron. It hit on inner shell electron and that ejected, then a hole will be here. So the atom wants to go to the stabilized state. So it will take one electron from the outer shell. So the outer shell electrons having more energy. So to get it stabilized, it release some energy in form of X-rays. So that is called characteristic X-ray. That's X-ray we measure, we detect using EDS detectors and then measure. So that's a unique X-ray. So we can identify the element because each element is having significant like unique X-ray energy. By measuring that X-ray energy, we will get the elemental information. That is what happening in EDS. So this is the thing that's happening in EDS. So this is the EDS spectra that we are getting in SEM as well as TEM. These are the EDS mapping. If we have the STEM and EDS with our TEM, then it's possible for elemental mapping. Elemental mapping means in EDS, we will get the elemental information, and from STEM, scanning transmitted electron microscope, we will get the positional information. So every point they took the EDS data. So it knows what are the elements present in that spot and then map it. So these are the EDS mapping. In this, you can see the colors. It determines the elements, but there is no specific color for elements. We are giving whichever color we want, we will give to the elements. That's the color of this mapping. And then we will move to the instrumentation part. Is there any questions regarding this TM analysis? Is there anything? Is any doubt? With the TM, it is possible. Like if you are using STEM, high resolution STMs, like atomic level electron microscopes, you can directly see the holes, line defect, point defect, everything you can directly visible there in the lattice pattern. But for that, we should have aberration corrected STEM or atomic resolution microscopes. Crystal defects can be, we can see there, but this kind of vacancies, I'm not sure. Is it in the atomic level? Then it's possible. Because our advanced electron microscope, they can show up to hydrogen atoms vacancies. That much, because that's the smallest atom. Those electron microscopes are capable of showing hydrogen atom. And like if there is some hydrogen atom is missing, that also we can show there. We can see there. I'm not much experienced with those high-end machines. So this is like common knowledge for me. Like it's possible to identify hydrogen atoms in this that level only my knowledge, because I have no experience with that high-end machines. In our lab, we have a 200 kV lab 6 type microscope. In that, we can go up to lattice fringe level. That's a just high resolution microscope. But this kind of work we can do with aberration corrected STEM or atomic resolution microscopes. Yes. line defects we can identify from our normal TM higher resolution images. Yeah, it's possible. But for these vacancies, it's difficult. In SAED patterns. Yeah, that is because of the direct image. Because in SAED aperture, we get scattered electrons as well as transmitted electrons. That is so we are using one beam stopper. You see here, this is the beam stopper because here it's very bright area, so that is affect the brightness here. So in software there is a compensator. So if there is something bright, then all the other dark regions got disappears. So we are using this beam stop. Okay. So we can move to the instrumentation side. Before that, in this operation mode, everything clear, right? This like imaging mode, SAD mode, lattice mode. Yeah. In this one, this is some single crystal material. Yeah, you see this direction. I cannot say all the details because most of the samples are not belong to me. I just analyzed some samples. So the sample information may not be not to me. That's this. Yeah, that is just for comparison, like single crystal, polycrystalline, and amorphous. Just for a comparison. That is like different crystals. For different crystal, different planes will be there. So it depends on the planes, the pattern will be different. For different material, we will get different patterns. That's the thing. So in instrumentation side, I will just explain what are the parts. Okay. In 10 minutes, we will just pass this section. Because in here, first is the electron gun part. So you know what is electron gun, but there are different types. That's why you are here, you know about SEM and FE-SUM. So what is the difference? The difference is the gun. In FE-SUM, they are using field emission gun. In normal SUM, they are using thermionic gun. That is the difference. So these are the electron gun region. Commonly used microscopes are thermionic gun type. But for high resolution, we are using field emission type. In thermionic type, we are just heating up the filament and we draw electrons from the filament. There are two types. One is tungsten type. Next is lanthanum hexaborate type. I'll show you this. These are the electron guns commonly used. So these are the thermionic gun and these are the field emission gun. So in here we are applying high electric field to draw electrons. Then these are the filaments that are used in different types of gun. This is the tungsten filament. This is the lower resolution microscopes filament. This is the lab 6 lanthanum hexaborate crystal. This is a ceramic crystal. We place this in the tungsten filament and then that heated up the tungsten filament. So the crystal will get heated up, then it emits electron beam, but the beam is more coherent and more bright beam will get from lab 6 than this tungsten type. But in case of tungsten tip, we are getting very high bright, high coherent, low wavelength beam from this field emission guns. So we are getting high resolution for this field emission than this thermodynamic type. Okay. Next is the column. In column, there we have lenses, condenser lens, gonio section, objective lens, and then projector lens, intermediate lens, everything in this column region. This is the main part of our transmission electron microscope. In this region, we are having very high vacuum. The electron beam generated here. Here is the electron gun, and this pass through this path. Okay. This is a very narrow path. It's like just like our refillers. That much small path is there. So the alignment is very crucial. If there is some alignment mistake, then we cannot see the beam here in the fluorescent screen. There we are using a fluorescent screen because we cannot see electron beam. So we are using one fluorescent screen to see the electron beam. So next is the high voltage tank. So there we are using DC voltage, high voltage, that is DC voltage. So in this, we are in transformer, we are giving this AC voltage, and through this diode, it gets charged like that, it's multiply. So in the first positive peak, it's conduct this diode, and then here this portion gets charged, and the next cycle, next section, likewise, this is multiplying the voltage. This is how we are generating high voltage in a transmission electron microscope. Next is the vacuum system. So this is very important. There are two types of gauges they are using for measuring high vacuum inside the microscope. There are Pirani gauge and Penin gauge. And then pumping system. So this is the pumping system that we used in transmission electron microscope, scanning electron microscope and all. And one thing is that there we cannot use any moving or vibrating motors inside TEM or any imaging thing. Because of the vibration, it will disturb the analysis. So first we are using this rotary pump for rough pumping from this room atmosphere to 10⁻³ torr. In electron microscope, we are using the term torr to measure the vacuum inside. So this pump is capable to pump up to 10⁻³ torr. So we call this a roughing pump. It's a mechanical pump with moving parts. So we will keep this outside the microscope. We cannot keep it inside. Next is diffusion pump. This is like here we have oil, heat it up. Then here is our column. Okay. So this jet comes through, the vapor jets comes through this portion, and because of this flow from the low concentration to here is the low concentration where some maybe some air or some particle, dust particle, something is there. So here is the more concentration area is the column. So from there it will flow to this region, and this our mechanical pump this out. This pump is capable to pump from 10⁻³ to 10⁻⁵ torr. So these two pumps are commonly used for scanning electron microscopes. And this one is sputter ion pump, or sometimes we are using turbomolecular pump. The name we have sputter. So the thing happening is that we are using very high voltage here, and it will ionize is something there, like particles or air molecule, something is there, it will get ionized and sputter coat on the surface of this pump. So if we use the microscope in very bad condition, because the life of this depends on the handling, like if there is more contamination or something, so the life of this pump get reduced, because it's you sputter coating on this, and more coating is there, then the efficiency will be low. So it's like for it pumps up from 10 raised to -5 to 10 raised to -8. Okay. So this is a high vacuum system inside the TM, and then there is another cryo pump that is we're using for to reduce contamination, because electron beam, it's a very high energy electron beam that can damage our sample. At that time, there may be that will affect the vacuum. So to overcome that issue, we are using a cryo pump. This is nothing. We just fill liquid nitrogen in this. So this is connected to near to the sample region. Okay. And here we place this outside this cryo pump, and then copper wires first to this sample region. So if some fumes comes there, then it will condense near to the coil. And after use, we will just heat it up. We called it as ACD, anti-contamination device, and there are ACD heaters. So we can heat the region and then take it out. The condensed particle we can burn out. These are the pumping system we are using in electron microscopes. So next is this electromagnetic lens. Here you can see the same lens, and then deflection coils to move the beam XY direction. So there are deflection coils, and this is how our lens look like. Okay. So this is the electromagnetic lens. Nothing, it's just a coil. So how we can control or adjusting the magnification as well as focal length? How it's possible? Current. Yeah, by varying the current. So near to the TEM console, you can see some console panels. There we have knobs. So by adjusting the knobs, we are changing the current. That's how we are changing magnification modes. And then aberration, everything by adjusting with coils, by changing the magnetic field. That's why most of the people are saying like we will not analyze any magnetic samples, because if we insert some magnetic samples, it may jump to the magnetic lens. Then it can affect the lens quality. So if we are normally using magnetic sample inside TEM, in future maybe we will have problem with lens. So the operator may struggle to get very good images. But in our lab, for the 12 years, we are using magnetic sample. We are analyzing. Because I am the only person who is handling, so I know the changes. So for me, that is not an issue. But after some time, we may have problem with the lens, because our group is strong with some magnetic study. So we have a lot of magnetic samples. So continuously we are analyzing magnetic samples. But this is the reason people they say like we will not analyze any magnetic samples. That's it. So it will affect the lens. So next is the goniometer section. This section handle the sample. So what is the thing we should take care about sample preparation? We have another section I will explain there, because here, this is the sample holder. So we need to insert sample into a high vacuum system. So how it happen? This glove box, how it works. So if you want to process or do something in some special atmosphere, like battery assembling, if you want to handle lithium, something like that, then we are using this glow box. So in a glow box, how we can insert things like our tools, materials, how we are getting take it inside, because there is a special atmosphere. There are two chambers separated with a shutter. So we can close this region and separate from this region. If you want to load something, then we will keep this in the chamber, close it, then create the same atmosphere what is there on the next chamber. Then open the shutter, take this. That is the thing. So the same technique that we are using here to insert holder, because we want to insert the sample to a high vacuum chamber. So if we open directly, then we drop this high vacuum inside. That's why we are using some airlock systems. First we inserted up to a level, then create high vacuum there, and then open the column section and then insert. That is how we are inserting samples inside a TEM. And this is the Gonier section. This is the sample holder. It's a long holder. It will go to this central portion on the optical axis. Okay. And this is the inserting mechanism. This is like first we insert the holder up to this level, then we pump, and then just turn this. There are some air locks are there to protect the high vacuum inside. So first we will just insert the holder and just turn, just insert and then turn, full insert. That is how we are inserting sample in the transmission electron microscope. So these are the different holders, and this is a TEM viewing screen.
वो इसके हिसाब से रख लूं 0.05 mm वाली
Glass opening.
रफली
So he can
वही हो गया ना 0.005
this is a fluorescent
हो
screen.
गया वही बता रही थी मैं यही
So
याद
here
कर
we
लिया
are using electron beam. We cannot
तो
see
वैसे लिख रहा
electron
है
beam
देखो
without
ना सिंपल इसमें कितना कुछ
So
कर
we are using this fluorescent screen to set the area of interest, because here we are projecting the sample to this fluorescent screen. Because of this fluorescence, we get a shadow image. If there is some particles in the sample, that side we will get shadows. With that shadow, we are
15
getting
पॉजिटिव साइड में है मतलब ये एरर
region
है
of interest.
ये आगे जा रहा है
So this is how we see the sample inside.
एरर देखो ना अगर मैं इसको
Okay.
ये बंद
This
कर
is the
देता हूं
normal view.
अब आगे
The low
निकाल
mag view,
पे टच
here
करा है
we can see the
नहीं ना
grid.
तो एरर है 0
In
से
the
आगे
sample preparation section, I will
माइनस
show you how we prepare the sample and what are the things we used for sample preparation, where we are preparing the samples like that. So these are the different magnification and images what we see in the
बेटा मैं ना ये बता के तंग आ
time.
चुकी हूँ कि ये फिगर
Okay.
ठीक नहीं है ये ठीक
So
नहीं है ये उल्टे
this
हैं
is the
प्लीज
viewing
मुझे
screen.
समझ लो
Here this is
तंग आ
the
चुकी हूँ मैं
Lomac.
बता के
Then
अब ये
we will
किसी से
just
समझ लो
choose
मेरा वैसे भी
this
प्रैक्टिकल क्लास
region
खत्म
of
हो चुका है
interest. This is
मैं बता के
here
तंग
we
आ
have
चुकी हूँ पर
some
आप गलती
rods.
करके डाल दो
Okay.
कॉपी हो
We
रहा है
see
इसका
this
मतलब
like
आप खुद
this.
से नहीं कर सकते
कितना है
First
0.05
we
खुद से
choose
कर रहे हैं
one region from this column. This is a 3 mm grid. Okay. With the 200 mesh. That is the commonly used grid in our lab. Say 3 mm 200 mesh copper grid with a carbon coating to support the samples. Okay. So here we choose this region, and there then we go for mag mode, because in that section I told you like we are using different mag modes. In low mag we will see like this. In mag mode we will see like this, and this is the diffraction pattern you see in this screen. This is how we are analyzing a sample, because you see the grid is something like, you see this button on the center, you see one white spot. That is the size of a M grid, and it's having 200 or 300 meshes. and one mesh is like this. Okay, and we choose this point. Only that much region we are analyzing in TEM. So it's very small area, very small area we are analyzing in transmission microscopy. Then image capturing, because we are getting the shadow image here, and we choose this region of interest, adjust everything like alignment, magnification settings, everything. After that, we just replace this. We move the screen. So what happened? The image goes to the camera. This is how we are getting image in the camera. First, we set everything, insert sample, then select the region, select the particle or rod or whatever the sample what we are looking for, and set the alignment, everything, and then remove the screen. Then the image we can see in the camera. In camera, we are focusing the image because here we cannot see the exact image. Here we can see the shadow only. That's we are using for the area selection, area of interest, something like that. Then these are the cameras that we use in TM. That it's a common CCD camera, but nowadays we are using this CMOS cameras because it's have very high resolution, but it's very costly than this CCD camera. And this is the EDS detector. This is a liquid resin cryogenic type detector. But now you cannot see this setup because now the detectors are liquid nitrogen free. So every time, like during all the analysis, we can use this EDX detector. But in our system, we are using this cryotype. So we should fill liquid nitrogen. In this, then only we can use the detector. So in our lab, maybe twice a month we are filling liquid nitrogen. But if we are having a liquid nitrogen free detector, then continuously we can measure EDS. So in here, there is a shutter. It's a window for there's electron trap, and then the detector, then the FET. So the X-ray goes to the portion, and then it's sensed by this detector, and this FET converted this X-ray to electrical energy, electrical signal. Okay. So from here, we will start our analysis section. So is there any doubt with instrumentation setups? Anything? Hmm? Yeah. So, hello? Okay.
So the doubt is, my sample is Ag doped ZNO in the ratio 1:10. In XRD, the characteristic peaks were present, but in the SEM EDS, zinc was absent. So what may be the reason?
The reason may be because in XRD, we are analyzing the bulk sample. When TEM and SEM, we are analyzing like very small sample. If it is a well dispersed or very good sample, then maybe in the analyzed region, there may be no particles of the zinc. That may be the possible reason. If we, in this case, we will check some other regions too. It's like 2-3 regions, we will take the EDS, then maybe we can see this zinc regions. That may be the possible because there is no other thing. There is no filtering or something, nothing is there. Yes. If you compare with XRD, that is the thing. In XRD, we are using very bulk amount of sample. In TM is very less amount. So that's maybe so less. Okay, so we can move to the analysis section. So in here, we should know what is the importance of morphology. Okay, because in nanomaterial, the property of the nanomaterials changes drastically with the morphology and size. That is the thing why we are going for transmission electron microscope imaging of your samples. Okay. So these all are the gold samples. You can see the color change. That is because the size changes and morphological changes. You see, nowadays we have this transmission electron microscope, but in ancient time, then also they are using these nanoparticles, but they are not aware about this nanotechnology. Because nowadays we analyze these kind of things, these glass paintings and this glass, then we found that they used silver nanoparticles with a different size. That's why they get different color. Okay. So now we have the tool, so we can identify things. If we can identify, then we can make use of this technology to some other extents. Okay. So that is the importance of characterization. We should know what is our sample, what's there inside, what are the properties, morphology, size, distribution, everything is important. So that's why we are going for this transmission electron microscope characterization of our nanomaterials. Okay, I will before that because I have the slides after this. Before that, I will just explain about the sample preparation technique. Okay. In just 10 minutes, I will just explain how we are preparing samples because sample preparation for transmission electron microscopy is very critical because we should have electron transparent samples. In SCM, you can use whatever samples. It's like you just want to cut down this to the working distance. Maybe it's maybe in centimeters. So it's very easy to prepare samples for SCM. The on criteria is that the sample should be conductive. The sample is not conducting, then we should make it conductive by coating some gold particle or some carbon something to avoid the cloud formation, electron cloud formation, and because of that we will get some blur damage. To avoid that, we make it conduct. But in TM, no need for conducting sample. But the thing is that we should have electron transparent sample. We should prepare the sample very thin, that is below 100 nanometer size. That is the preparation criteria. And the previous slide. This is the TEM grid that we are using to prepare TM sample. Okay, this is a standard grid. It's a 3 mm grid with 200 meshes. And there is a supporting film on the top that will support the powder samples, something like small nano materials. Okay. And we cannot load wet sample inside the TEM. Because of this, we cannot get samples. Only dry samples are out. If you have some liquid samples, then we will prepare this on the grid and then dry it. Okay, and then only analyze inside TEM. So first, follow this drop casting method. This is the simple method for TEM sample preparation. We just disperse the sample. If it is a liquid, it's a colloidal form, then we should just drop wisely add one or two drops to the grid, then dry it. That is the simple method that we can follow for TEM sample preparation. Only thing should be very low concentration, not very low. There should be something. But if it is a concentrated sample, drop casting. What is drop casting? In polymer film, we are following this drop casting method to produce polymer films. That is like we will just drop wise add some solvent or something and then just dry it, we will get a film. Okay, that is drop casting. We follow drop casting technique for this liquid and powder sample also. First, we should prepare a low concentration solution in a suitable solvent. Suitable solvent means the sample should not dissolve in the solvent. Okay, because if you want to analyze some sugar or salt crystals, what will happen if we prepare the sample in water? It will dissolve. So we cannot see the crystals. Likewise, we should choose the solvent suitable, like it will not dissolve the sample. Okay, that is the suitable solvent. Then uniform dispersion, not dissolve, dispersion. So we will just we took a little amount of sample in a sample preparation bottle, and then we use a suitable solvent and disperse it. So in here, what you see is a clear solution, and here you can see some particles settled here. Okay. So this is the first thing what we observe before sample preparation. If you have a very good nanomaterial samples, then you will get a colloidal suspension like this without any sediments. Okay. But in this here, you can see some particles were settled here. That is because all those are microparticles or bigger particles that will settle easily. For nanomaterials, it will not settle this much easily. Okay. That's the first thing. You just shake your sample or sonic it and then hold some time. You can see the particles coming down. So if it is happening, then your sample is having some bulk materials. And this is the method for drop casting, same method for powder sample. So we just crush down the sample and prepare the same, then drop cast on the grid, then dry it, sonic it. This is drop casting method. The next thing is ultra microtomic preparation. Because if we have some polymer samples, it's bulk polymer like rubber samples, epoxy samples, we are making composite using all those materials. Then we want to see this dispersion of the filler. If it is uniform dispersed or agglomerated or it's aggregate or something like that. So we should see the dispersion of filler material in the matrix. For that, we are following this ultra microtomy technique for section the sample. So this is the microtome arm. This is the setup. So this is the instrument. This is the eyepiece, because we are preparing sample in nano region, like nano slices we are preparing using this microtome. So this is the eyepiece to see the prepared slices there. Okay. So this is the arm. Here we are fixing our sample. This is the knife. So we will slice down the sample like this. This is a knife, this is the arm, it's moving like this. So if you set a 50 nanometer, so the feed is 50 nanometer. After each slice, the arm will come forward 50 nanometer. So the next slice will be 50 nanometer. So if we explain, it's very simple, like we just hold the sample and slice, but it's not that easy. Because the perfection of the slice depends the quality of image. If you have very good sections, then only we will get high quality images. So this is the ultramicrometry technique. These are also two types, one room temperature cutting and then cryo cutting, because rubber, it's elastic. So we should cut it in the glass transition temperature. You know what is glass transition temperature? If you put the rubber in some liquid nitrogen, then it will become brittle. That is glass transition temperature. So first we should take this to the brittle stage, then we cut the rubber samples. So that are the two types. So the normal type, and then next is cleaving. So this is like if you prepare something on glass slides, it's like something coated on glass slides, then we can follow. Not like this, because here they are saying like we just cut down the slice and then dissolve the background, then take this. Like if you painted on some clay or something and then just put it in water, what will happen? The clay will dissolve there and the painted thing will be remain as a film. So we just take this like that. And if we prepare this film on a glass substrate, then we cannot follow this method. So in that case, we are using this focused ion beam milling. Like we can cut the surface like this. So this is the surface. We will cut like this and analyze. Okay. This is also very costly equipment. It's about 3-4 crores if you want to go for the dual beam FAB. The transmission through microscope technique is not very common only because it's very costly. That's why. If you want to set up a transmission TEM lab, you need to spend nearly 6 to 14 crores for a normal TEM lab, because with all those sample preparation techniques, otherwise we cannot analyze some of the samples from your lab. That depends what work you are doing there in your lab. Okay. So this is the sample preparation method for biological samples like tissue samples or plant samples. This is not very easy, because if you want to analyze your cells or tissues, first we should remove this from the organisms or from the animal. The next moment it starts degrade. So whenever we collect the sample or dissect the sample, the next moment you should transfer this to a buffer solution for fixing. Because first fixing, because we want to keep this intact, then we should remove all the water content, because living cells, they're having a lot of more than 50% water content. So we should remove this water content. So first we fix it, then dehydration. After that, infiltration. Infiltration means we replace the water molecules or water content with the ethanol. After that, we embedded this in epoxy. So before embedding, we should replace all this ethanol with this our epoxy resin. So that is infiltration. After infiltration, we embed this in epoxy. So this is the method that we follow. After embedding, we will just cut down the samples. Then normal polymer analysis, like we will analyze the slices, sections. That is how we are preparing animal tissues or plant tissues in TEM. For sample TEM, it's very difficult for biological samples. So this is the purpose we are going for TM. So what are the things you are like? Can you identify anything? Because there are a lot of things are there, like there are very small particles are there, it's a well distributed dispersion, and then different morphologies from size. So in this image, you can identify many things. This is not a good sample, but this is good for explain why we are using this technique, because there are different morphologies there, different size, everything is there. In this part, we can maybe show this agglomeration. All those things are there. To identify all those things from your sample, we are analyzing, you are going for TEM. This is the purpose why we are using TEM technique. To identify the size distribution, aggregation, agglomeration, morphology, all those things. Okay. And the next is a very interesting image. So if you take this kind of picture as some so, but at that time, this is two rhinoceros. Okay. But in the beginning of this section, I show the projection things like that. We cannot identify the exact things, but we should observe the samples or images very carefully. Then only you can identify what is the thing is there. Because you should check many regions, then you will get the correct information, like what is your morphology, something like that. You see this in nano size, you feel like this is the shape of this material, but this is two different materials. So that's why the important of this thing. Here they say, like in real life we laugh, and if you see in this research we will publish something like that. So the meaning is that you should be very careful about inputting or analyzing your electron microscopic sample, because it's a projection image. So there maybe like error maybe happen. You see, if it is a cube, if it's directly project on the top on the axis, then we will show a square shadow there. Then what will happen if we tilted it? It's maybe we'll see like some pentagon or something like that. So we should be very careful about inputting 3M images. Then these are some of the morphology. This is the rod morphology. One more important thing, you should take care about the scale. Most of the people, they say like, sometimes they say like, oh, here this is 100 nanometer, so our particle size is 100 nanometer. It's not like that. This is the scale. So this is just for reference. Like here it is 200 nanometer. The length of this line is 200 nanometer. Wherever you measure, it's 200 nanometer. So that is the thing. And these are the different morphologies. This polymer blends. In here, the dark region is the more dense region, dense polymer. This is the low dense polymer. In here also, so we can see the major phase and minor phase. We can see filters, everything. This is another blend composite. Here, the interesting thing is that in sometimes due to the polarity, the filler goes to some regions. So to identify the filler dispersion, we are going for TEM analysis. And then this all are other. Here we have CND. This is clay. This is carbon black, graphene, and CND. That is CND alone. That is layered silica. And these are the quantum dots, zero dimensional material. It's very difficult to get these kind of images because this is very light material. So we cannot see these particles on the fluorescent screen. So blindly we are searching for a good region. With the help of camera image, we are getting this kind of images. So it's very difficult to get this kind of images for QDs. And this is the electrospun fiber. Here this is the electrosomal fiber. In SEM, you can see the surface, but in TEM, like our X-ray, it's a cross-sectional image. You can see the particles inside the structure. Okay, that is the difference between SEM and TEM images. This is the core shell. And these are adsorption, like once some particles adsorbed on the surface of some other materials. This is the bacterial sample. In this, they explain like they used some silver nanoparticles. So here we can explain the limitation of like optical microscope. In optical microscope, we can see this bacterial samples, but we cannot see this silver nanoparticles. That's why we are using transmission microscope. Here, they put some silver nanoparticles and analyzed after 28 hours. They got that bacteria. So these are difference. In TEM, we'll get two-dimensional image. In SEM, we will get three-dimensional image. Here you can see the internal structure, cross-sectional structure. That is the difference. In SEM, you will get surface image. Okay. So these are some disadvantages, like it cannot take color pictures because we are not using light. Color depends on the light, so it cannot take color images. We cannot analyze thick samples. Sample preparation is very difficult, and these are the things. So you know how to use image. Okay, then this is a free software. This is the one of the main tool that we are using to measure particle size distribution, all those things. So you see, for TEM image analysis, nothing is there. Whatever you see, that is the result. Like if you see rods, then our morphology is rod. If it is sphere, then morphology is sphere. So only thing is that we should measure the size or the dimension we should measure. For that, we are using image. So I don't. I will show you because there are a lot of tutorials are available. It's very simple. You just load the sample and then main thing is the scale. Okay. Then first we set the scale. Should be very careful about scale settings. Okay. I'll just show you how we can. Okay. Hello. First, we should share one image. It's the same image should. Yes. Hello. So, shall we start the image analysis for silver nanoparticle in image A? So, open image software in your laptop and then load this AGTIF file using this file button. But I don't instead. Here's the image. Isn't that desktop? Hmm. Hmm. Okay, എല്ലാരും load ചെയ്തിട്ടുണ്ടോ? You know how to load the file there in the image software. It's like just open a file in any other software. Like just go to the file, open, or just drag the file to the window. It will open. Okay. I hope all you have this file. It's shared in the WhatsApp group. Just open this in image. Okay. So after that, we should set the scale using this analyze window. Can you see this analyze window there? So there you can see set scale. Before going to set scale, you just take that set scale. Then in that window, you just clear all the remaining scales. Yeah, please remove the scale. And then go to the main window. There you can see a line tool. I hope all of you following. So shall we proceed? Okay. So first we open one file. I'll show you here. Open. Let's stop right. What's the file? AG. I'll drag it. Alright. So first you open the file and then here first go to analyze, reset the scale, reset scale, click to remove scale, then select the line tool here. Then okay, I will show you there. Oh, okay. Okay. First go to the set scale, then clear scale. Okay. Select the line tool. Okay. Then zoom in the scale. In the way. Minimize ചെയ്തിടാവോ ഈ സ്ക്രീൻ ഷെയറിംഗ് അതിനകത്തേക്ക് പോകുന്നുണ്ടെങ്കിൽ ഓക്കെ okay, select that zoom tool and click on the scale. Then select the line tool, draw a line above the scale. So be careful about the starting point and end point. Okay. First you load the file, then reset scale, and then zoom in the scale because to reduce the error, maximum zoom your scale bar. So it's easy to find the starting point and end point. Okay. And draw the line above the scale. Just control and scroll button can use for zoom in and zoom out. Okay. So for analyzing, you first open your images software, load the file, and in analyze menu, just go to the set scale option. There, reset the scale, and then zoom in. Okay, zoom in, then select line tool, draw a line. Okay, and then again go to the analyze menu, set scale. Okay, so there distance is pixel, that's we select the line, that's the pixel, and then next is non-distance. So there on the scale there is a reading, it's 100 nanometer. So non-distance is 100. Non-distance 100. Then you set unit. Unit is nanometer, nm. And then take the global button, then OK. Now we set the scale. So this is the first part. Okay. So then select the line tool, and then you can draw wherever you measure, like whatever you want to measure, you just draw the line above that structure. Okay. Then there are two options. Maybe you can go to Analyze tab and then click on Measure, or you can simply choose Control M, the short key. So if you press the short key Control M, it will show the result. It's like length. There are a lot of results you got in the new window there. We choose this length. That is the size of the line, like the line length, that is the size of the particle. Okay. It's a very simple software to measure the particle size, but there are a lot of other options are there. Image processing, distribution curve. We can plot this distribution curve. There are two methods. One, we can plot this distribution curve by measuring each particles, but if its number of particles is more, then it's difficult manually marking all the particles. In that case, you can use the particle analysis method. You can follow this. There are a lot of simple YouTube tutorials are available for image. In that, they are simply explain how we can use this software like that. So now you know how to set the scale and measure the particles, right? Okay. So you choose many particles and measure. Minimum 30 particles should be there to plot a histogram or particle distribution curve. Okay. So maximum particles you measure, and then in the file, there you can save. In the result window, there you can see this file menu. There you can save the results. Okay. So you can save this in Excel format. From there, you can choose the length column, and using your origin software, you can plot the histogram using that length. Okay, you got it. So is there anybody having issues with measuring the particle size? It's very simple. Just set the scale wherever you want to measure. You just plot the line, then measure. That's it. And if you want to retain the line, just press Control D, draw. So the line will be there. It's like if you want to mark the particles and label the size, you just draw the line there, keep it there, and then there you can label the size of the particle. For labeling, you can use this alphabet menu here. Here you can label. So have you saved the result? If you save the result, you will get a Excel sheet there. And using this length scale, you just plot this in using origin. In origin, you just open the worksheet and paste this result, and then just plot the histogram. You will get the particle distribution histogram. Yes. Now, from the image itself, it's very clear. You can identify if there is something error or something. You can see the particles from the scale. Yeah, you can. It's about 15 to 25 nanometer distribution is there. Okay. I will explain that. Okay. Length മാത്രം മതി. Only length. Just plot in Y. And then go to histogram. Histogram. Not familiar with this origin. Yes, 30 to 35. Around 2 particles are there. 40, 3 particles. Yeah. This okay, so there is one doubt how to measure the magnification. So, how to say what is the magnification of this image? So, is there any information regarding magnification? Can you see anything? The only thing is that there's a scale. So, we can measure the scale using a scale. our scale, in centimeter scale. Okay, so if it is 4 centimeter, actual size is 4 centimeter. This no, image size is 4 centimeter. Actual size is 100 centimeter. 4 centimeter divided by 100 nanometer. That is the magnification. 4 centimeter. If it is 4 centimeter or 5 centimeter, if it is 5 centimeter, then 5 centimeter divided by 100 nanometer. That is the magnification. But in SEM, you can see the magnification there on the image itself. But in TM, the problem is that the instrument magnification that is showing there in the operation window is up to viewing screen only. The camera is some more lower. So if the distance is more, the magnification will be very high. That's why we cannot mark the exact. There is a magnification we can see on the operator menu, on the control menu, but that is not the actual magnification of the image. So if you want to check the actual magnification, you can calculate this from the scale. Yes. So the same method we can follow for SAED pattern indexing. Okay. So in SAED patterns, we can see the spots. Okay. Here you can see the diagonal spots. With this, we just measure from here to here. For every ring, we took the diameter. So the easiest way is that in digital micrograph, the other software that we used for microscopes, in that, what the specialty of a circle is that there is only one diameter will be there. Okay. So if we choose one point and we can measure the other side for the diameter. In one point, we will have the maximum value. So that is the diameter. So in SAED pattern, the d value is 1 by r. So we know the diameter. So diameter by 2, we'll get the radius. That is the r value. So 1 by r. R is the d spacing value. So using image J, you just measure this diameter, then calculate the radius, and the inverse of the radius will be your d spacing, and check that d value with your ICDD data, you will get the planes. So that is how we are interpreting SAED patterns. Okay. So next, and then there is another method we can measure the particle size of each particle, but it's very difficult. Its method is simple. Sometimes it will not work. That's the problem. First, we should set the threshold. In here, first go to the image file, then check the type. Sometimes it may be the RGB color file will be there if you choose some screenshot or something, because in image A, you can select the region of interest, because for this type of analysis, like if we want to plot the particle size distribution curve, then we should choose a region with well distributed particles with clear boundaries, like well separated with clear boundaries. Then only the software can easily analyze the data. Sometimes it shows some error. So the best way is to measure manually all the particles, and then using that length result plot the histogram or the distribution curve. Okay. So for more understanding, like you can follow tutorials. It's available in YouTube. Very simple tutorials for different analysis. Like this, then you can process your images. It's like you can improve the quality of your images using Image. There are a lot of tutorials available. Next, I will show you the other software that we used in microscopy is Gatan Microscopy Suite, a digital micrograph software that commonly used for acquiring microscopic camera images that we capture through that Gatan microscopic suite. So that's not free software, but for data analysis, we can use that software, but we should have the instrument file. With that instrument file, you can check all the operating conditions of the microscope, like magnification, then operating voltage, brightness, everything. You can check with that digital micrograph software. I will just show you. Can we stop this image section? Because now you know how to measure the particle size. So maybe we can move to other. Then I will show you one more thing to check the d-spacing. Okay, I will just show you how to measure d-spacing. So I just load one HR image in here. We just set the scale. So here I just set the scale. Here the starting point I am not sure, but it's almost set. Then set scale here. The known distance is 2 nanometer. So I put 2, unit is nanometer. Okay. Okay. So here the easiest way to choose 10 places 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it should be perpendicular to the planes. Okay. Then measure. So here we got 4.56. So this is for 10 lines. So for the d value will be the length divided by. So this is 0.45 nanometer. So this is how we are measuring d spacing. More number, error will be less here. So I am stopping this image section and then we'll move to this digital micrograph. There is one interesting thing is there. You can upload this FFT image that is very clear. We will get very clear lattice fringes image for low quality from low quality lattice fringes images in the that what we get from TM. So we can improve the quality of lattice fringes using that digital micrograph software. Oh, this is not the paid version, so the toolbars are not visible here. So I should find the tools. Mm. Eight, 4, 1, 6, 0. Okay, so here I opened one lattice fringe image here, and using this profile, I got this. I can select here and then spread this using Control plus. So I put this width to 10, maybe more, maybe 100. Okay, so I spread this, then I choose some better area. So now it is perpendicular to the planes. Okay. So from here, all these peaks corresponds to the fringes. Okay. So here, from here 1, 2, 3, 4, 5, 6, 8, 9, 10. So here it's like 2.0364. This is another file. Okay. So this is another method to measure the despacing using digital micrograph. And then there is, I am not familiar with this window. That's why, because in my software, we have all the tools here. There's a toolbar. It's a paid version because we are using with the TM. So all the tools are available there. But in this window, most of the tools are not there. Next is the Fourier transform. So here first we should select. I choose this region. Then in process, I took the F50, but it shows the F50 for all the whole image. But no. Okay, so this is the F50. Here we can see some, the spots is here. You see, you can see the spots. You should use some maps here. So I choose this. I map these points and then in process apply mask. So these spots are correspond to the diffraction spots of this corresponding lattice fringes. Okay, so I selected that spots and keep the mask area. So we removed all the other areas. So and then go to process, go to the inverse FFT. Where is inverse FFT? You see here. This is how we can enhance the lattice fringes using digital micrograph. Okay, so you just install your digital micrograph free software in your laptop. Just load your lattice fringes image, and then you, if you want to select the region, but it's not works here, so I don't know why. But you can choose the region somewhere. If it is very clear, you choose that region, and then in process take this F50, and then using that on right click you can see the tools. Okay, and then you choose that selection tools for this diagonal spots we can select, and then apply mask. After masking you just keep the masked area only, and then go to the process menu, take the inverse F50, you will get the enhanced image of this your region. Yes, there is no data with me because I'm not doing my research here. So I just analyzing some samples. If you want to do something like this or you want to check this, you can directly contact me. I will help you. So if you want to analyze any of your microscope nanomaterials, you can directly contact our office or me, IIUCNN. It's in Mahatma University campus. And you can find our facility in ISTEM. The slot booking is available there. And then there's a registration website and payment site. For colleges, it's 4,000 per sample, 4,000 rupees per sample for analysis. And another 700 or 500 something for ADS, 1,000 for ultramicrotome, depends on the sample and requirement. So first you book your slots in ISTEM, and then registration and payment. After payment, you got this requisition form and submit your samples with signed requisition form. Yeah, we will prepare your sample from outside. We took the grids and we prepare and we will analyze. We will send you the result. And during analysis, you can sit with us and you can see what is happening there. You can select the region. You can see what are the other possible areas. Like in TEM, if you send the sample to some other lab, they will send you some 10 to 20 images. But if you go there and sit with the operator, then you can see the other areas. Because you send a sample and you will inform them like you are looking for some rod-like structure, then they will concentrate for this rod-like structure. They will search everywhere there in your sample. And if there is some rod morphology is there, then they will capture that region. But maybe there are some other interesting morphologies will be there in your sample. Maybe different size particles may be there. So a lot of things you can see in the TEM, not in your image. So it's better to sit with the operator if they allow, then that will be better. Yeah. Yes. Don't go directly like after synthesis. First, you thoroughly check your sample. First, check with UV. If the peaks you got in the exact position, then you can confirm there. And then the purification, like the pure sample will give better quality images. Okay. So, and if you have some images, then we will get some idea about the morphology and all. Then go for TEM, because in TEM we are analyzing very small region, and we can find different morphology, different types. It's like it's a you are searching something on a stadium. Okay, you are looking for a motor pin, like small pin in a stadium. The sample inside TEM, it's enlarging anything like a stadium, like this 3 will magnify up to that level, because it's the maximum magnification is about 1.5 lakh times. Okay, so we should have very good idea about our sample, then only we can easily get some good images, some like useful images, because some images that will explain themselves, like you modified some material and you got this, so you show this image, the image will explain it, the thing that you modify, it's there, so no need to explain more. For that kind of images, you should explain the operator, like I am doing this, I am expecting this, then you will get that kind of images that will help you in publishing high index journals, like uh, that high quality journals, they will expect that kind of high quality images. Okay. Okay, any doubts or anything? Oh, ഇത് കൂടുതൽ എൻഹാൻസ് ചെയ്തിട്ടുള്ള, അതായത് നമുക്ക് ഇതിന്റെ ഒറിജിനൽ ഇമേജ് കണ്ടായിരുന്നോ? എൻഹാൻസ് ചെയ്തിരിക്കുന്നതാണ്. കാരണം ഒറിജിനൽ ഇമേജിൽ നമുക്ക് ബൗണ്ടറീസ് ഒന്നും അത്ര ക്ലിയർ ആയിട്ട് കിട്ടില്ല. അപ്പോൾ ഫോറിയർ ട്രാൻസ്ഫോം വെച്ചിട്ട് നമ്മൾ ശരിക്കും നമ്മൾ ഒരു പോസ്റ്റ് പ്രോസസ്സിംഗ് ആയിട്ട് ചെയ്യുന്നതാണ്, കൂടുതൽ ക്വാളിറ്റി റിസൾട്ട് കൊടുക്കാൻ വേണ്ടിയിട്ട് അങ്ങനെ ചെയ്യുന്നത്. Okay, so I hope all of you understand about something about transmission electron microscope, and what we are doing with microscope, and what we are getting as images for results, and how to interpret all those things. So I hope if there are no more questions, then we can conclude. Okay. Is there any question online? Is there any doubts or anything? Okay. Okay, thank you.
Thank you, sir. That was an incredibly detailed presentation. To conclude this segment of the workshop, I invite Dr. Paulo Suti Abraham, one of our participants, to share their reflections and offer the vote of thanks.
Good afternoon, everyone. On behalf of participants and audience, it's my pleasure to propose a vote of thanks to Mr. Anil, Technical Engineer, sorry, Anu, Technical Engineer, MG University. As a part of Indian research community, we often face a criticism that we lack the essence of spirit of inquiry and scientific temper. So after the second chapter of this workshop, I think we are all rekindled with this essence, and we hope we can communicate, we as a participant and audience communicate to you, Anusa, for future research endeavors. So first and the final, and we and us really appreciate your time and effort to be here with us with your immense knowledge and experience. So without further ado, I thank to Department of Physics and Stephens College, Uruvur, to have such a wonderful experience, and we are very keen for the next section. And thank you so much. Thank you.
As a gesture of our sincere gratitude for this enlightening session, I request our IIUCNN coordinator, Ms. Humbly Catherine Thomas, to please come forward and present our token of love to our resource person. All participants kindly move to the back of the hall for a photo session.